Monsanto is a company that is known for its chemical and biological engineering. It is less well known for its data science and software engineering teams. Tim Williamson is a data scientist at Monsanto, and on today's show, he talked about how he and a small group of engineers created a cultural shift at Monsanto around data science-driven genetic engineering. In this episode, Tim explains how useful graph databases are for modeling the genetic lineages that Monsanto works with. And he talks about how Monsanto uses simulations and experiments on their software genomics pipeline. He also talks about how a few engineers can create a cultural shift within a large company like Monsanto using the leverage allowed by software. After we hear from a sponsor of Software Engineering Daily, we will get into the weeds of Monsanto data science. As a software engineer, you have tremendous leverage in the employment market. Every company needs software engineers, and these companies are all competing for you, the engineer, a scarce resource. But as an individual engineer, you don't have much insight into this incredibly opaque market. That's where Hired.com comes in. Hired.com assigns you a talent advocate who works to understand your needs and works to find you the perfect job. Go to Hired.com/SEDaily to try out the platform today and get a $2,000 bonus if you find a job. The companies on Hired compete for you, the engineer, and they make bids to win your talent. These are companies like Facebook and Uber, companies that we know are on the cutting edge of engineering because they've come on Software Engineering Daily to talk about their tech stack. I've used Hired personally, and I've experienced firsthand the ease of finding a well-paid, enjoyable job. This was way better than replying to LinkedIn messages from uninformed recruiters, and it was also certainly better than using a job search engine. To find a great job and support Software Engineering Daily, go to hired.com/SEDaily and get a $2,000 bonus upon finding a job. Check it out. It would support the show. Now let's get on with the show. Tim Williamson is a data scientist at Monsanto. Tim, welcome to Software Engineering Daily.
Thanks for inviting me. I'm really happy to be here.
Yeah, it's awesome. So 6 years ago, you were working at the biomedical department of Washington University in St. Louis. What compelled you to make a career transition from academia to industry?
Well, that was at the biomedical engineering department at Washington University was my first job out of grad school. And at that time, I was really gung-ho on this idea that I was going to go the academic research route all the way. And at the time, I was working in a lab that built large-scale parallel processing software for molecular modeling. And I got really heavily into software engineering and data science at that point. And I kind of started looking around and thinking about where I could work, what I could do that would have a bigger immediate impact to the world. I had this sort of, academic midlife crisis. And I came to be aware of Monsanto, which is a big employer in our region, and I got really interested in the idea that one of the great problems that's going to happen in my lifetime is how does the planet figure out how to feed the sheer number of people that are going to be here over the next couple decades. And I thought that is a problem that I can work on and own a piece of, and I went for it. And I made a pretty big shift from academia to the corporate world.
So why is data science important to Monsanto?
Data science is important to Monsanto both because we are a large scientific R&D company, which means by definition we gather a large amount of quantitative data, more so than can be processed intelligently by hand. And more importantly, the size of our R&D pipeline has just become so large and so fast-paced over the past 10 years as we try to produce better and better products on a shorter and shorter timeline that we have had to figure out ways where we can design algorithms and data structures that allow a lot of the scientific decision-making to be automated down to where our key high-value scientists are really only looking at that small percentage of a problem that really requires an expert.
And Monsanto has been around for a long time. I want to eventually get into the software processes and things that you've been working on. But one thing that I find interesting, Monsanto, I think it's been around for more than 100 years. And for many years, most of the engineering was about chemical and biological engineering and management. But software has increased in importance more recently. How did the engineering organization shift to one that can take advantage of high volumes of data and software?
Well, I think so. I've been here 6 years, and I would say that most people would define Monsanto as being a heavy genomics company and seed company since about 1995. When we dove into genomics and the company quickly had to become a leader at the cutting edge of that space, I think we were on the exact same trend as a company that the rest of the biomedical and genomics community has been on. The cost of generating high-value genomics data, DNA sequencing and genome fingerprinting has dropped precipitously over the years, so much so that the cost of gathering the data isn't the rate-limiting step anymore. It's more of a storage and an inference problem. And we, as a company, way above my pay grade, we had to make strategic decisions that if we were going to keep up and innovate in that space, we had to significantly change our headcount and how we organize.
Very interesting. So how does the biotech side of Monsanto and the chemical engineering side interact with the software engineering side?
So we are a science R&D company, not expressly an IT company, which means we have a large IT and software engineering organization that builds platforms by which those pipelines operate over, which is where I sit. So, for example, my job and the job of my immediate team is mostly to build back-end data science and engineering products that local data science teams in scattered across various R&D groups can tap into to accelerate their decision-making. So myself, my team, and many others build back-end systems that end-user data scientists can tap into. So we build our own internal platform that our local data science teams tap into to pull data out of, to execute decision-making algorithms, to run machine learning, so on and so forth.
Do the data scientists that you build products for, do they tend to have a background in biology or chemistry or science, or do they work, if they don't, do they work closely with people that do?
So I don't know I guess I would like to think that we are special in our needs. However, I think that the gamut of skills that our data scientists have is probably not any different than any other company of our size, which means it's broad. Data science is kind of a really funny, hard to pin down term, and it manifests itself here. So we have a lot of data scientists who are heavy domain experts. In fact, their primary training is in that of the domain. So graduate training in genomics, biology, chemistry, biomedical engineering, so on and so forth. However, we do have a subset of data scientists that come in from a straight statistics or applied math background. And what's generally happened here is we have formed a higher level academic community around data scientists. So there are those of us that have significantly more skill in engineering and algorithm design and implementation. There are those of us that are domain experts, and those of us that are not necessarily domain experts nor programmers, but hardcore statisticians. And almost every important project that I've ever worked on has involved a combination of individuals from all of those backgrounds. Mm-hmm. Now, cross-training is definitely something that is difficult and we try to spend time on, but I don't think we've yet to assemble a team where everyone on the team is that mythical unicorn data scientist that does everything.
Okay, so it sounds like you have the T-shaped people, as we've discussed in Software Engineering Daily on other episodes.
A good example of that might be the fact that in the genomics space that I work in heavily, we'll often have a couple genomics researchers that are sort of at the cutting edge of the literature in their field that are working on trying to adapt how we can apply a particular algorithmic observation to a large data set. But the team will come together pretty early on in that process to try to work at the early prototyping stage and make sure that scales to our backbone pretty quickly. And we found that's the only way we can keep up.
So I want to ease into a conversation of how you built one of these tools that you exposed to the data science teams working throughout Monsanto. And you gave a talk at the recent Graph Connect conference in San Francisco called Graphs Are Feeding the World. And you discussed the evolution, the construction of this tool that has become widely used by teams at Monsanto. What were you trying to convey in that talk?
Oh, wow. So many things. Hopefully some of them well. I was trying to convey the fact that, data science, particularly in the life sciences and the hard sciences space, requires really deeply thinking about how you shape the techniques and the data to the problem that you're solving. In addition, I was also trying to communicate the fact that there are a lot of really what should be high-profile problems that a lot of people, very smart, educated, excited people, don't commonly get exposed to. So in that talk, I was trying to tell a story about how we built this fairly specialized data processing pipeline that very much matches the space of the scientific data we're trying to process, but telling it in the context of, hey, I think that this problem of how we are going to feed the world is an important one, and it's one where people working in software engineering can have an outsized impact. I want to tell the story and hopefully get a couple more people interested.
You said in that talk that we've gotten very good at making targeted modifications to the genetics that we want, and we're going to make the next step change in food production in the near future due to a completely data science-driven genomics pipeline. How is this different from how we've made improvements to food production in the past?
So I think it's an evolution of scale and quantity of data that can be mined to yield a better quality inference. So when you look at the core way in which new crops are developed, whether they're at Monsanto, any one of our competitors, or any number of academic research institutions, you are essentially relying on a knowledge pipeline that has built up over the past several hundred years of plant breeding. So a scientist working in a field will decide that they want to breed a plant that resists some disease. And at the same time they resist the disease, they also have to perform really well. They have to be cheap to produce, they have to yield well, they have to be easy to harvest. And they're going to achieve that by identifying plants, males and females, that can be crossed together to potentially pass on those traits, and then examining the offspring and seeing which ones are the best one. This is a workflow that's been persistent since the days of Gregor Mendel. The difference is now, in the world that we live in, we are increasingly trying to develop agriculture products that are targeted to very specific environments. So we don't just want to sell, for example, corn that grows well across all of Iowa. We want to be able to sell seed that performs particularly well in a particular field, which is some combination of soil and moisture and weather attributes. And to do that would require making a significantly larger number of crosses, inputs, which our pipeline can't handle. We can only horizontally scale so much. And therefore, our position and what me and my team and others work on is, well, how can we rank that possible space more efficiently to only make the crosses and only pick the plants that have the highest probability of the outcome that we want?
To get an idea of how this tool, this set of tools, or this API was constructed, we need to get into some of the domain-specific ideas or domain-specific data structures that you work with. Could you explain what a genomics pipeline, for Monsanto, at least in terms of Monsanto, what is a genomics pipeline and what is a breeding cycle?
Sure. So the easiest way to level set everyone, no matter what your background is to this problem, is to think of your own family tree. So the inside of a plant genomics pipeline looks like a larger and messier version of the same family tree that you might look up for yourself on Ancestry.com. That's essentially what how our pipeline's structured. So the start of a breeding cycle is something that occurs many, many times over within that pipeline. So within that genealogy, to use a more domain-specific term, you're going to have plants, sets of plants that you can cross together. And we call those plants parents. So if I decide to use 2 plants in a cross, I'm going to call them parents just to use some more common verbiage. And I'm going to choose those plants because both of them possess some set of qualities or traits that I want to have in one progeny. So one plant might be resistant to a disease. One plant might be susceptible to that disease but grow really well. And I want one plant that grows really well and is resistant to the disease. So if you think about that, when I cross those parents and I get many, many progeny plants, many, many seeds out of it, I can screen those plants using a variety of genomic and physical techniques. A good example of genomic technique that we use all the time are various levels of DNA sequencing or DNA fingerprinting, where we're trying to make some observation of the structure of that plant's genome. That way we can make a decision on whether or not it's a winner. On the physical side, we might actually go out in the field and make an observation. This plant is, in fact, resistant to this disease or not. And then at every round of selection, we're only picking the ones that we want and letting those go forward and have offspring, and we're dropping the ones that we don't. So over time, over many, many, not just years, but many, many cycles. So if you think about it, we could get about 4 planting seasons per year, depending on where we ship seed around the world. That builds up a giant family tree that over top of it has information across the tree around at every node, at every point in the tree, what traits we've observed about it and what genetic data that we've gathered. And that forms sort of the base data structure that we try to draw inferences across.
So are you needing to grow and monitor each of these generations of plants, or can you simulate things?
Well, we can do both, and we're increasingly trying to simulate more. So a good example, and that's what I talked about in that Graph Connect talk, is where now that we've kind of figured out how to treat our pipeline as a dense genealogical graph and draw inferences across it, where do we go next? And this other and the area of pipeline simulation comes up. So I mentioned that, and it's fairly widely known that the price of actually fingerprinting something genetically, sequencing it, has dropped a lot. But it doesn't mean it's dropped a lot if you have to characterize genomically several million seeds a year or a month. That's still not enough. And even if it did start to drop really close, it doesn't mean it would be a worthwhile investment. But it turns out that you don't have to necessarily sequence something to know everything you need to know about it genetically. So again, walking back to your family tree structure, plants, just like humans, if you cross 2 plants, just like if you cross two humans or 2 mammals, the progeny are going to be 50% male and 50% female genetically at some high abstract level. Now, rather than assess every progeny at a really high level of detail, using a lot of money and a lot of time, it turns out that if you intelligently run quicker samplings of the genome, so maybe instead of sequencing the entire genome, only sequence it at targeted places that we work very hard to figure out where those are, you can actually use the structure of the genealogy. So what are my parents? What do I know about my parents? What have I measured about my progeny? To simulate high-resolution data that is good enough to make an informative selection on the progeny. And that's something that we've worked quite a bit at.
Okay, got it. So whether you are simulating or growing real plants, as I understand, Monsanto models the lineage of its plants, or you can model it at least, as a directed acyclic graph. Or maybe not necessarily acyclic, depending on how you look at it, but certainly a graph. And each vertex is a plant species, and each edge between those vertices is a transition across a generation. Is that accurate?
Yes, except I would go a little bit more detail and say that each vertex is not just a plant species, it's an actual single individual, so a seed.
Okay. Oh, wow. Okay, very interesting. So with that in mind, I mean, I guess this is kind of a softball, but why are graph databases useful for Monsanto?
Well, hopefully if you know a little bit of something about graph databases, we've already kind of figured out why it works really well. In this particular case, it's like I mentioned earlier, it's an example of where we can actually select a storage technology that maps back to the physical domain as closely as possible. The reality is that data set is, by any rational description, a directed graph. And by choosing to do the engineering and the modeling work to store all the data that way, we obtain both an extreme computational efficiency in operating over it, but more importantly, we obtain the ability to be far more expressive about our data set. So when you're doing genomics research, any graduate level genomics textbook will be full of graph descriptions of how traits are inherited, because that's the way the science works. And therefore, more and more our back-end data systems match that mental model, it's significantly easier to do high-end development work.
Yeah, there was actually in that talk you mentioned flipping through a biology textbook and finding a paper from like 1921, I think, about poultry breeding, which it illustrated the usefulness of graphs applied to genetics that has, like, since 1921. So it's been around forever. It's been a core, I don't know if the geneticists would call it a data structure, but it's been a data structure that geneticists think of and use for a long time.
Yeah, in that example, I mean, personally, I like old science textbooks. I think it's really, as a hobby, I think it's really fun to go back several decades and take a look at a field that you know very well and think about where it was. And in that case, you're right. There was a really that was a poultry breeding textbook from 1921. They were trying to describe in a mathematical way how I can describe a child as a summation of all of its ancestors, and had drawn out a really nice diagram describing what we now today would call co-ancestry as an algorithmic concept. And it was drawn out as a graph long before anyone really understood really deeply in the life sciences what graph models were. And now fast forward to today, we actually people have built databases that we can use to model that data along the exact same mental model. I think it's fun.
This is a bit of a deviation, but I rarely talk to somebody who spends time flipping through extremely old biology textbooks. Do you ever find would you ever like be flipping through an old biology textbook and you see like somebody trying to write a paper about like the scientific justification for leaching, or like some like really weird scientific process that now makes absolutely no sense, and they're trying to justify it because that was a thing in some anachronistic scientific process?
I have personally never encountered one, but I've heard stories like that. One thing I think was interesting is any textbook that sort of predates the early 1900s. At the time when scientists were first studying DNA, they assumed DNA were proteins. We had no idea that the unit of inheritance was something different. So it's amazing to see what's different. Even now, I was an undergrad. I started my undergraduate work right about when the Public Human Genome Project, they published a draft genome. And to think about how the entire field and all its ancillary support structures has changed since I was an undergrad, and I like to think that I'm not old, is really humbling.
Engineers are always looking to simplify. To simplify testing and deployment, engineers turn to CodeShip. CodeShip is continuous integration and delivery as a service. With CodeShip, your tests are executed against your code automatically whenever you push to GitHub or Bitbucket. On Software Engineering Daily, we've done several shows about DevOps, and continuous deployment is key to DevOps. It's a great way to break down the wall of confusion between development and operations. Managing your own testing infrastructure is painful. That's why you want a service like CodeShip to do it for you. If you have a huge number of tests, you can use CodeShip's Parallel CI to run all your tests in parallel. CodeShip will spin up containers on their own infrastructure to run your tests in parallel. If the code passes your tests, CodeShip will deploy it automatically to your users. Companies like Product Hunt are already using CodeShip to speed up and simplify development. To sign up for free and start shipping today, go to codeship.com. Or to try out CodeShip's new Docker platform, go to codeship.com/Docker. So, one of the ways that you characterize, we can talk about like in the abstract that, there's a tight relationship between the physical structure of the data and how you want to use it in the database, but you benchmarked this in a way that was like pretty convincing. And so one way that you characterized why graph databases are so useful to Monsanto is you talked about this operation, just a very basic prototypical operation. Given a starting population, return all the ancestors of that population. Makes total sense for somebody like Monsanto who's doing lots of genetic work. Could you explain this query and contrast how the performance of the relational database compared to that of the graph database?
Sure. So I said at the beginning of the talk, Monsanto's been a plant genetics company since about the mid-90s. So, since then, we've accumulated years and years of generational advancement, so adding more nodes to that tree, generating more seeds. And also over that time, we've bought intellectual property, we've bought other companies, and our pipeline's expanded. All along that time, we were gathering this genealogical data, but it was being stored pretty much if you thought about how you would model what is a dense graph in a relational database, that's how we did it. So we had a large number of what are commonly called join tables, so parent-child tables in a relational store. We'd store all this data in, and then if we wanted to analyze it, we would execute some essentially what I like to refer to as a really, really nasty connect by prior query in SQL space. So connect by prior being the operators that you use in SQL to do nested joins. And we would run these queries in a sort of a warehouse-style fashion to assemble these genealogical trees that would go into data mining operations. And this is all well and good to a small on a small data set, but it quickly becomes unmanageable because I think it would probably be really obvious to most of the listeners of this podcast. The join operation scales really, really ugly as you do more and more joins. And so what I showed in the Graph Connect talk is if you take a pretty standard lineage and you look at it and you benchmark it, assessing from the same starting point, can I build its family tree back to some levels of depth? In this case, we used up to a depth of 15, which is actually pretty small for a plant breeding pipeline. And we measured the performance unloading the data from our relational stores versus the graph version that we had produced. And it was pretty shocking that I think we were observing at the end almost a 90-fold difference in performance. And what I thought was interesting about that graph algorithmically is that when you look at the scaling, it pretty much behaves as you would expect from Big O notation. So the join bomb, you hit the join bomb, you start this really nonlinear scaling as the number of joins goes up. And the graph store, one of the fundamental properties of a graph database or evolving, because it's a really rapidly evolving field, is that you should be able to achieve what's called index-free adjacency, which means I should not have to take a join hit to go out to my neighbors, and you actually see that in our benchmark, that the scaling is flat.
Oh, wow.
And what's fascinating about that from a data science standpoint is that for us opens up a really different space that we can work in. Because now I don't have to judiciously choose to only analyze a small set of populations because I only have so much CPU time. If I want to, say, analyze the genealogical structure of our entire North American corn pipeline, that's possible now.
So once you realized that you could get these types of performance gains out of graph databases, what were the types of higher level abstractions that you were able to build on top of that graph query interface?
Sure. So to start off with, me and my team fundamentally believe that if you're going to build a really cool data science product for data scientists, the answer isn't build a really awesome database store, throw it out there, and then expect everyone to learn yet another strange query language. It's never felt right to me. So we kind of went the route of, we're going to have this backend data store, and we're going to layer on top of it a REST layer, a query layer, where the objects are defined in terms of things that people working in genomics and plant breeding are used to dealing with. What not only are they scientifically meaning to them, they know what they are, which means they know how to work with them when they're pulling them into their own analysis code. A classic example is what I alluded to earlier when we were talking about measuring genomic data versus trying to simulate genomic data. So in a plant breeding pipeline, just like in a mammalian breeding pipeline, the act of a male and a female crossing to yield progeny is called, it's a two-way cross, a binary cross, but it's also has a special status of being a recombination event. That means that two distinct lines, two distinct genomes have merged together, and therefore there's been a sampling from both. So that finding that feature in a large data set reliably is the underpinning of all of the work that you might do if you're trying to simulate genotyping. So that's a good example. Is expressing that in SQL is extremely cumbersome, unperformant, and doesn't look at all like something a geneticist would recognize. But simply being able to hit a REST resource and say, I have this population, give me its most recent binary cross, that's something that our standard domain scientists can work with without really any frustration. And then beyond that, you build from there. All types of common crossing patterns can be represented in the same way.
So I'd like to talk a little bit more about this idea of that you should really consider the type of API that you're exposing to whoever your data science customer is. We did a show with a company called YHat where they're essentially building an entire company around solving this problem, where they're building a product that allows software engineers to easily expose an API to their data scientists. So they've seen this problem time and again. How should, from your perspective, what are the broader lessons you learned here in terms of how software engineers should be interacting with the data scientists that they are building products for?
So first, I listened to that episode, and I enjoyed it quite a bit. Those guys are really fun to listen to.
Yeah, they are.
At the risk of using a cliche, that is a very interesting question. And it's one that I've thought about a lot, my colleagues have thought about a lot, because I think that this space of data science versus data engineering versus analysis is really, no one really lays claim to it, and it's not nailed down. My intuition, for what it's worth, and what we try to operate on, is that the relationship must not be combative in any way, and in fact must be as frictionless as possible. So I think when I started, there was 6 years later, no one's really defined exactly what data science is, but in the beginning, I think there was an adversarial relationship between, all right, we have these domain specialists, we have statisticians, they know a lot of really interesting things, but they're terrible at doing development and nothing they write actually works. Therefore, we shouldn't really spend too much time working with them, versus your very traditional software engineering team, which can build and implement something very efficiently, but of course, the time sink for them is figuring out what the correct thing to build and implement is. And that's sort of the really swinging weight of software engineering. I think for us, all the meaningful problems have broken open when the friction between those teams have gone away entirely. So for example, if you think about, again, simulating genomes, right? The reality is that, as good as those of us who have become more dedicated data scientists and data engineers might be, we're not going to be as up to date on the literature as one or two scientists that have spent their entire academic careers doing that and now work here. So we rely on them to wade through the signal and the noise of the science, but then work very, very closely with us to ensure that what we are iterating towards can actually work at what we call pipeline scale. And in fact, we're fond of saying that the coolest algorithm that someone could produce at Monsanto is really worthless if you can't process an entire crop pipeline at once. You're not going to gain the type of inference that you need to actually make a business impacting decision. And that attitude drives what we do now. So again, if our primary consumers are going to be people applying our data science products to genomics problems, then the surfaces by which they interact with, which just might be a REST API in this case, has to have little to no impedance mismatch with the way they think about the data. And by doing so, they're happier using the product, they can use it more efficiently. We're happier building the product, we can use it more efficiently, and so on and so forth.
So the service that you ended up building is called Ancestry as a service. At least it's an internal service. Describe this service to me.
Okay. So Ancestry as a service is first of all, nothing's cool unless you call it as a service. So that's where that came from. It is a service which is implemented as a REST API where scientists, data scientists, software engineers, development teams can make REST calls into it against objects that match their domain. So for example, ancestors, descendants, binary crosses, so on and so forth. And they get back payloads, which represent the result of executing some number of algorithms against our graph store in order to provide the answer to their question. So a great example would be that product serves both software engineering teams at Monsanto as well as data scientists. Going right back to the genomics example, the labs that we use to generate genomics data are highly automated, and therefore that means that we need to have machine automatable ways of quality controlling data. And the way that we do that in genotype space is that if we know the genotypes of a set of parents, and we're running several million progeny from those parents through the lab, the machines that are QCing that data will actually call out to Ancestry as a service to fetch all that parental data in order to make a determination on whether or not the data that I'm seeing coming off the machines even makes biologic sense. So every meaningful genomic element in our pipeline, we have either expressed or are trying to express as a basic REST resource.
Give me some idea of how this API has improved the workflow for the data scientists who consume it.
So on the data science side, I think there have been two major areas of improvement based on the level of experience that the data scientist has. So for experienced data scientists, and not just experienced data scientists, but experience at the company, because every large company has very different ways of managing their data. Therefore, there's a certain amount of impedance mismatch as you jump from company to company. For those that were used to working with our old data stores, there's just been an efficiency gain in the size of the problem that they can handle and the amount of data munging that they have to do to get their data sets. So that's obviously a key performance metric for doing work like this. What I actually think is more fun is newer data scientists, or data scientists that are moving from one domain of the company to another. So now when, say, we make a brand new hire, some awesome data scientist from some marketing company comes to take a job at a science company for the first time. Well, if they are able to interact with a complex data set in terms of very basic biological concepts that their colleagues can teach them, which they can now, the rate at which they can become productive and leverage the skills they bring in against our biological data sets becomes significantly easier to climb. The activation energy is a lot lower. So those are really sort of two kind of basic examples. On the more complex side, now that we can actually ask bigger questions of our data sets in a meaningful amount of time, we're currently undergoing this phase where we're actually reopening some ideas that have been shelved over the past couple of years that just weren't deemed tenable biologically because of the state of our data, and asking ourselves which ones of those can we actually do now.
Can you give me an example?
Sure. So going back to genomic simulation, ideally, what you want to get to is, so right now we have a pipeline where we might have a bunch of parents, make a bunch of crosses, do a bunch of selections, trial a bunch of seed products in different environments, and then try to make a recommendation based on where you're going to grow the seed, what is the best one to buy. That's a very standard pipeline for agriculture genomics. What we'd want to do is flip that on its head. So think about it, not necessarily look at what crosses do I have the ability to make in the pipeline. Ask myself, if I want to develop a product that is most optimized to grow in Central Valley in California, what parents can I cross in what way to have the highest probability of success of achieving the end result that I want? So that requires doing, so essentially what you're trying to do is become prescriptive about what crosses that you're making. And that is an area that we hope to make a lot of progress in. It's extremely data heavy. It should work intellectually. Intellectually, it can work with the right data set and the right machine learning, but that's a great example. We'd love to get to a point where when we could look at a plot of land and, make some quantitative measurements of the state of that land, and then actually not just recommend an existing product that would work the best, but go back into R&D and say, okay, we believe that this is going to be a major stressor. I like to reference water loss in California a lot. If we think that drought tolerance is going to be really, really important in these soil types, we should be able to bias our R&D pipeline towards producing products that will have that result.
Okay, so that's super promising, interesting example. So I want to talk about this system. A Monsanto engineer built a system that uses Spark that enables estimating the genotype of any seed that goes through your genotype pipeline. Could you explain how this works in more detail?
Sure. Actually, I'm hoping in another couple of months or so that we'll actually be able to get him to put together a public talk on this, because I think it's a really interesting use of the technology. But essentially, when we talk about genotype estimation, you really have a couple inputs that you need. One is if you need to know, I am a population, what is the path back in genealogical space, what is the graph structure to the last time that I had some quantity of genotype data in my lineage. That's a tree structure. Tree structure with annotations that indicate where I have that genotype data. And then I need that genotype data, which is another data set at the company. It turns out that if you combine those data sets together and you walk down each cross in that tree, you can make a probabilistic estimate of what were the most likely combinations of the chromosomes of each parent to essentially estimate high-resolution genotype data of your progeny. So a way to think about that is we know at a high level that if I cross a male and female, that my progeny is 50% male and 50% female at a really high level. But we know that it's not alternating across the genome. There's certain fractions of your genome tend to segregate together. Well, when we take a low resolution data set, we try to map across that in an informative way such that we can estimate the gaps, estimate the rest that we didn't measure. The way that was achieved technically is that there are a variety of published algorithms for doing that operation. It's commonly called genotype estimation or imputation in the literature. We have an engineer, a data scientist, who developed what we believe to be a better version of that algorithmic technology. And then to scale it to the size of the several million progeny going through the lab in a given year, we chose to implement it by performing all the genomic, the probabilistic analysis in Spark over graph data structures that we spit out from our genealogical platform.
Okay, that's awesome. That sounds super interesting. I'm looking forward to hopefully that talk, if you can convince him to give a talk on that. So I want to talk a little bit about how you were able to get this project off the ground, this Ancestry as a service kind of movement within the company, because it sounded like it took some significant cultural shift Was the graph database project, was this part of like a skunkworks initiative or anything, or how exactly did you get such a large scale shift off the ground?
So, in a sort of a high level retrospect, we're a large scientific research company, but that's a lot different from being a large scientific IT company, like a Google or a Facebook, which means that the number of people that are comfortable with essentially skunkworks style development work is significantly smaller, which makes doing really, really big, super innovative projects difficult sometimes. We address that problem in an under-the-table sort of way. So prior to me and my teammates working together, we all worked in different parts of the company where our common thread was we were banging our heads against actually working with these genealogical data sets in any meaningful way. And we happened to get together over some shared pain, and we decided that, there has got to be a better way to do this. Every time we work with this data, we end up sucking it in and building in-memory graphs. Surely someone has figured out a way to actually persist these on disks so I don't have to keep rebuilding them. And I know oddly, it seems odd to think about it that way, but we decided that, there were a number of graph databases that we could use, and that started everything off. And then once we realized that there was a chance to do this, we took a day at work, and a free day that we were granted, our version of 20% time, and built a really promising prototype that solved one particular problem in one day very, very quickly. And then at that, we were hooked, and we were having a lot of fun. So we spent, for the next 3 months, most of our nights and weekends working on this. So we were doing skunkworks development work for our company, but on our own time, oddly enough. And by the end of that, we were able to make a product sort of an early version of the product that worked for our entire pipeline. And we showed it off roadshow style to essentially our version of internal investors. So the leadership teams that are capable of making funding decisions, just like you would if you were an external startup, and it got funded, and that's where we are now. I think that particular story really isn't that exciting for most people unless you do have the experience of working in a large company whose primary focus isn't software development, and that's how we dealt with it.
I think one of the key lessons there is that you have an idea for something in a big company like this, you have to build a prototype oftentimes to really convince external stakeholders that this is not vaporware.
I completely agree. In fact, the term that we like to use internally and I think maybe this is a common term, is we don't want to be boxes and arrows people. So a box and arrow person is someone that draws a really great whiteboard diagram, but will never actually achieve the product that they're doing. And people that are in positions in a company where they can allocate money are very aware of those people. And I think you're right. For any meaningfully complicated software data science project, you have to be able to prove that it isn't vaporware, that you know what you're doing before you can reasonably expect someone to invest in you. And I think the real world, obviously that works. That's the way the real world works.
That's true. Absolutely. Execution is everything. Your ideas really don't mean anything. So, I want to zoom out. Our time is drawing to a close, and talk about some higher level things. So there's been a boom recently in agricultural software technology. Like if you look at Y Combinator companies or just companies in the Valley in general, are there any companies or products that are really exciting to you these days? Like what do you think is illustrating the future of this ag tech, I think is the category people talk about, or agritech?
Ag tech or agritech, I've heard both. First off, I'm really excited. I think that this is a really fascinating space to work in that has many variables at play, and there are many different problems that can be worked, all the way from a level of a very large global company to a small startup. It's ripe for innovation. Things that I think are the most exciting, I think there's two general areas of work that I think are most exciting, and I don't really have enough knowledge of the startup scene to know the players in each one, but I know that there are many companies out there at different sizes going after it. One would be on the far end of the pipeline, so delivery of a product to a farmer in the space of what are called decision advisors. So I am a farmer. I have so many acres in such and such a place on Earth. How can I use a data science-driven product to effectively give me the path through all the decisions that I will make during a growing season such that I can maximize my return, both in terms of not just what to plant and how much to water it and how much fertilizer to use and so on and so forth, but when to harvest and when to sell. So people forget that profiting on a farm is not just about growing as much as possible, but almost no grower can actually store all the product that he harvests, which means that there's a very short window from when he harvests that he has to go to market. And when he goes to market, he's going to get whatever commodities different prices available on that day. So there's really a lot of fascinating work on the economic side of how can I actually inform a farmer, knowing the window that they have, to maximize profit. So those decision advisors, I think, are fascinating areas of work. The other one is what I alluded to earlier, is how do you make increasingly more targeted genomic decisions in order to yield products which will do best in an increasingly complicated environment. So how do you mine all the data that you're gathering on the farm across a particular set of microenvironments, particular soil conditions, particular weather conditions, to better make decisions in a breeding pipeline to yield seed that will better perform in that environment? That's an area that's ripe for innovation.
So speaking more on the latter side of the two types of categories you mentioned, we did a show recently about Soylent, and Soylent is kind of interesting. They have this moonshot vision that's sort of like you have like a bioreactor that grows everything you need, and then it just, I guess, pipes whatever food is growing to your food faucet. And then so you have the future is like you have a water faucet and then like a food faucet. As somebody who thinks a lot about biological engineering as well as how to execute on that stuff at scale, is this something that is inevitable in our future where we have this as an option, and is it how realistic is it?
I think realistic scientifically is different from realistic socially. I just to wax poetically about the field, and I think for the majority of people in the world, food is more than just the sum total of the science that's used to create it, even though it's highly scientifically driven. People like to eat. They like the experience of eating. They like what happens around them socially when they eat. So I definitely think that technically and scientifically that vision is achievable completely. I'm not sure how far off we are, but I definitely believe that you can engineer someone's nutrition very completely. And I'm almost positive that, especially as we become a society that or humanity moves farther and farther, hopefully into space, which I would like to see, those advances will become more important. Do I ever think that type of nutrition will unseed people's cultural expectations of what it is to eat and what it is to be hungry and be full? I'm not sure.
Is it desirable or realistic to move towards a meat-free nutrition model? And can we get the types of benefits that we get from proteinaceous meat consumption from reconstituted corn and stuff, or is this out of your pay grade?
I'm definitely not a dietitian or nutritionist. So I have no idea. Although I will say that,
can graph databases solve this problem?
No, not that I know of. I'd have to go to the publications for that. I do think, though, if you want to think about another sort of more out there intersection of ag tech and the Soylent model, I do think we're probably going to see some interesting advances over the next decade in the synthetic meat area. So lab-grown meat. I do think that'll be a thing.
Mm-hmm.
But
certainly. Okay, so final question. I want to ask a question. It's not closely related to software, but We often hear the term GMO, which means genetically modified organism, and people have kind of been trained to react negatively to this term, but we've been doing genetic engineering for centuries, as you mentioned, the days of Gregor Mendel. Ever since farmers learned that they could select which types of corn were yielding better characteristics. So I know there's some misunderstanding around this term, but my question is, like, do you think there is any risk associated with GMOs, or do you think there is potential risk that is aggregating or compounding as we selectively evolve the organisms that we're modifying with more aggression?
That's a very deep question. Very simply, no, I don't. I believe that the science that we use to make these modifications and test them is sound and testable and rigorous. I think that the vast majority of what we do, which is why breeding is so fascinating, is it's essentially a more automated way of doing what we've done for hundreds of years. It's just that now, instead of necessarily having to observe every plant to check what we want, we have the ability to screen it genetically, and so on and so forth. I actually think that as the world of tools that are available for making genetic modifications and assessing genomic content further mature in the areas of extremely precise modifications, a la CRISPR. I don't know if you've heard a lot about that, but that's been in the news.
Sure, absolutely.
I think that the pace and precision and quality and efficacy of research will actually get better than it is now. Will continue to get better as we continually become more aware of how to make the selections that we want efficiently and in the more precise manner.
Awesome. Okay, well, that seems like a great place to close off. Tim, thanks for coming on to Software Engineering Daily. This has been a super fascinating conversation. I'm glad we got to discuss the intersection of biology and data science and software engineering.
Thank you for having me. This has been a really great experience, and I'm a real fan of the work that you've done.